Hello and welcome back. In today's video, I'm overclocking the AMD Ryzen 5 8500GE APU all the way up to 5225 MHz using the ASUS ROG Crosshair X670E Hero motherboard and custom loop water cooling. This is the third Hawk Point APU that I'm overclocking on this channel, following the Ryzen 7 8700G and the Ryzen 5 8600G. However, the 8500GE is the first Phoenix 2 APU I'm overclocking, and the Phoenix 2 is significantly different from the two other Phoenix 1 APUs because it has Zen 4 as well as Zen 4 C cores on the chip. Now, that makes it very different in terms of clocking and voltage topologies. And there's a bunch of other things related to Phoenix 2 that makes overclocking it quite interesting. I hope to explain all that in this video, and I hope you enjoy the content. Let's get started. The Ryzen 5 8500GE is part of AMD's Zen 4 based Ryzen 8000 desktop APU product line codenamed Hawk Point, which was introduced on January 8, 2024. The GE SKUs were quietly announced about a month later. They are the same as their G counterparts, but rated at 35 watt instead of 65 watt. Side note, oddly, I can only find the Ryzen Pro version of this APU on AMD's website. However, my APU is recognized as a regular non-Pro Ryzen. Hawk Point is the successor to the Ryzen 5000 Cezanne APUs launched in 2021. The Ryzen 8000 series APUs come to market in two distinct configurations. APUs with the Phoenix 1 die only have Zen 4 cores, while the APUs with the Phoenix 2 die come with a mix of Zen 4 and Zen 4C cores. A lot has been said about the difference between Zen 4 and Zen 4C cores. The core architecture is identical, while the Zen 4 cores have a smaller footprint. The benefit is that you get more compute per area, but the trade-off is that you also have higher hotspot temperatures and lower frequencies. In AMD nomenclature, you'll find that the Zen 4 cores are referred to as classic cores or C cores, and the Zen 4 C cores are referred to as dense cores or D cores. Throughout this guide, I will also refer to them accordingly. To support the classic Zen 4 and the dense Zen 4 C cores, the clocking and voltage topologies of AMD Phoenix 2 are very different from that of Phoenix 1. I'll dig very deep into those topics in the final overclocking strategy. For now, suffice to say that the Zen 4 and the Zen 4C cores operate at different frequencies and have different frequency limiters. The Ryzen 5 8500GE has 2 C cores and 4 D cores with 12 threads. The base frequency is 3.4 GHz and the listed maximum boost frequency is 5 GHz. The TDP is 35 watt and the TJ max is 95 degrees Celsius. In this video, we will cover 3 overclocking strategies. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. In March 2023, I launched the EFC SkatterBencher edition in collaboration with Elmo Labs. The EFC SB is a customized version of the original Elmo Labs Easy Fan controller. The base product functions and features are the same as the original EFC, with a tiny improvement here and there. I also used the device to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then, I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course we have to look at the performance at default settings. The default Precision Boost 2 parameters for the Ryzen 5 8500GE are as follows. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU C-core effective clock is 4162 MHz and the average CPU D-core effective clock is 3330 MHz. The average CPU core voltage is 1.024 volts. The average CPU temperature is 53.6 degrees Celsius. The average CPU package power is 42 watts. When running the OCCT CPU SSE stability test, the average CPU C-core effective clock is 4424 MHz and the average CPU D-core effective clock is 3539 MHz. The average CPU core voltage is 1.108 volts. The average CPU temperature is 56.0 degrees Celsius. The average CPU package power is 42 watts. Of course, we can increase the maximum power consumption by leveraging the Precision Boost Overdrive toolkit. That's exactly what we'll do in our next overclocking strategy. But before that, make sure to locate the CMOS Clear button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling Precision Boost Overdrive and AMD EXPO. With the launch of Zen 3, AMD introduced an improved version of the Precision Boost Overdrive toolkit, which allows us to fine-tune the parameters that affect the Precision Boost boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost Override and Scaler, Precision Boost Overdrive 2 also introduced Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we are just enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and, to a lesser extent, the TDC and EDC limit will help unleash the frequency in multi-threaded workloads previously limited by the PPT. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that enables ubiquitous memory overclocking on AMD platforms that support DDR5 memory. Essentially, it allows memory vendors such as G.Skill to program higher performance settings on the memory sticks. And then you can enable that higher memory performance with the click of a single button. So it saves you from a lot of manual configuration. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO Tweaked. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Surprisingly, despite increasing the power consumption headroom from 35 watt to 1000 watt, we only get minor performance improvements in most benchmark applications. The geomean performance improvement is plus 1.96%. When running the OCCT CPU AVX2 stability test, the average CPU C-core effective clock is 4614 MHz and the average CPU D-core effective clock is 3690 MHz. The average CPU core voltage is 1.199 volts. The average CPU temperature is 74.4 degrees Celsius. The average CPU package power is 71.6 watts. When running the OCCT CPU SSE stability test, the average CPU C-core effective clock is 4625 MHz and the average CPU D-core effective clock is 3699 MHz. The average CPU core voltage is 1.207 volts. The average CPU temperature is 67.1 degrees Celsius and the average CPU package power is 59.3 watts. The boost frequency at one active thread is about 5050 MHz and stays there when up to 4 C-core threads are active. When D-cores become active, the average boost frequency gradually trails off to 4036 MHz when all cores are active. The 2 C-cores can boost to 5050 MHz and the 4 D-cores can boost to 3.7 GHz in single-threaded workloads. In our second overclocking strategy, we fine-tune the CPU frequency using the Precision Boost Overdrive Fmax Boost Override and Curve Optimizer tools. And we also optimize the memory subsystem just a bit. Fused Maximum Frequency, or Fmax, is a precision boost infrastructure limiter that defines the maximum allowed frequency for your CPU cores. Boost Clock Override, or Fmax Override, is one of the overclocker tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit between -1000 MHz and +200 MHz in steps of 25 MHz. It's important to note that the Fmax override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. For most Ryzen processors, we don't actually need to explain that much about the Fmax Boost Override. But because Phoenix 2 is so unique with Zen 4 and Zen 4C cores, we need to detail it a little bit more. The C cores and D cores are functionally identical, other than the D cores running a much lower frequency. The two types of cores are part of the same core complex, or CCX, so we'd expect they run at the same frequency. However, that is not the case. For each of the two core types, there's a 1T and NT maximum boost frequency. The default 1T maximum boost frequency is 5050 MHz for the C cores and 3700 MHz for the D cores. When configuring the Fmax boost override, the 1T Fmax increases linearly. So, for example, if we set plus 150 MHz boost override, the new 1T max frequency is 5200 MHz for the C cores and 3850 MHz for the D cores. The default NT maximum boost frequency is 4625 MHz for the C cores and 3700 MHz for the D cores. Configuring the Fmax boost override adjusts this frequency ceiling, but not linearly. For example, if we set plus 150 MHz boost override, the new NT max frequency is 4775 MHz for the C cores and 3820 MHz for the D cores. That's respectively 125 and 120 MHz higher than stock. For your reference, I plotted the 1T and NT Fmax for the C cores and D cores. We'll discuss this graph in greater detail in our next overclocking strategy. Curve Optimizer is an important new tool of the Precision Boost Overdrive 2 overclockers toolkit. Essentially, Curve Optimizer allows end users such as you and I to fine-tune each core's factory fused voltage frequency temperature curve. The voltage frequency, or VFT curve, is essentially a curve that defines what voltage is required to run a certain frequency at a certain temperature. The higher the frequency, or the higher the operating temperature, the more voltage is required. Curve Optimizer adjusts the VFT curve by offsetting the voltages of that factory fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. You can offset the entire curve by up to 60 steps in a positive or negative direction. Each step represents approximately 5 mV. The traditional overclocking approach with AMD Ryzen CPUs is to use a negative curve optimizer. Two things happen when you do that. First, we effectively undervolt the CPU and tell it needs less voltage for a given frequency. And, as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage for a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. Like in the past, per-core tuning offers a real benefit as it provides some cores with a lot more frequency headroom. There's no practical difference in the curve optimization process for the C cores and the D cores. The manual tuning process for Curve Optimizer can become quite convoluted because it spans a wide range of workloads, going from light, single-threaded workloads to heavy all-core AVX workloads. I usually spend quite a bit of time trying to find the best Curve Optimizer setting for each CPU core individually. Here's my broad approach. Once all the testing is done, I run through the usual benchmark suite and stability tests used in this guide. If there are no instabilities, I consider my curve optimizer settings as stable. On AMD Hawk Point APUs, the memory subsystem consists of three important parts: the Infinity Fabric, the Unified Memory Controller, and the System Memory. They're more commonly referred to as the Fclock, the Uclock, and the Mclock. First generation Ryzen overclockers know that these parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 5 8500GE, we can tune them independently. There are two things that I wanted to address when it comes to memory subsystem performance optimization. First, I wanted to fix the downclocking of the Fclock and Uclock, and second, I wanted to run the Uclock and Mclock in sync. To solve the first problem, we can simply enable SoC Uncore OC mode in the AMD overclocking submenu. This disables all power-saving technologies affecting the clock frequencies of the memory subsystem. To address this second problem, we simply set Uclock div1 mode to Uclock equals memclock. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. We run the memory controller frequency in sync with the system memory for this OC strategy. At DDR5 6400, the memory controller frequency is then 3200 MHz. EXPO Tweaked is an option available under the ASUS AI Overclock Tuner setting. It's similar to EXPO 1 and EXPO 2 as it loads the EXPO profile, but does so slightly differently. Since memory performance may impact our benchmark performance, I tried the EXPO Tweaked setting. Everything seemed stable, so I used it for this OC strategy. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO Tweaked. Switch to Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set Uclock div1 mode to Uclock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency Timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO Limits to Motherboard. Set CPU Boost Clock Override to Enabled. Set Max CPU Boost Clock Override to 150. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. For every core, set Curve Optimizer sign to negative. Set Core 0 Curve Optimizer magnitude to 0. Set Core 1, 2, 3, and 5 Curve Optimizer magnitude to 25. Set Core 4 Curve Optimizer magnitude to 20. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to Enabled. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. While we aren't able to maximize the Fmax Boost Override overclock due to C-core headroom, we can undervolt the D cores significantly using Curve Optimizer. This yields a nice performance uplift in both single-threaded and multi-threaded workloads. The geomean performance improvement is plus 6.87%. We get a maximum improvement of plus 16.13% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU C-core effective clock is 4748 MHz and the average CPU D-core effective clock is 3799 MHz. The average CPU core voltage is 1.199 volts. The average CPU temperature is 74.3 degrees Celsius. The average CPU package power is 84.9 watts. When running the OCCT CPU SSE stability test, the average CPU C-core effective clock is 4752 MHz and the average CPU D-core effective clock is 3802 MHz. The average CPU core voltage is 1.199 volts. The average CPU temperature is 68.3 degrees Celsius and the average CPU package power is 71.5 watts. The boost frequency at one active thread is 5200 MHz and it stays there when up to 4 C-core threads are active. When the D cores become active, the average boost frequency gradually trails off to 4167 MHz when all cores are active. The 2 C cores can boost to 5200 MHz, and the 4 D cores can boost to nearly 3.8 GHz in single-threaded workloads. In our third overclocking strategy, we leverage the return of Eclk mode. Eclk stands for external clock, and it's exactly what the name suggests. It's the ability to use an external clock generator. This function was also available on Ryzen 2000 processors, but was later removed until Ryzen 7000. Now, I've used Eclk in a lot of my Ryzen 7000 overclocking guides, but it's the first time that I'm using it with an Hawk Point APU. Considering the difficulties or the complexities related to the AMD Phoenix 2 architecture, before we talk about Eclk mode, let's first have an in-depth look at the Phoenix 2 clocking and voltage topologies. The clocking of Phoenix 2 is similar to other Zen 4 CPUs. The standard Phoenix 2 APU has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the SCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by a frequency ID or FID and divided by a divider ID or DID. As a whole, this provides a core clock frequency granularity of 25 MHz. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. On Phoenix 2, the C cores and the D cores are part of the same core complex. However, the D cores operate at a significantly lower frequency. And that's counterintuitive because we've always learned that the cores within a CCX should run at the same frequency. I'll get back to that in a minute. The SoC PLLs include a wide range of PLLs. The ones most relevant for overclocking are the Fclock, the Uclock, the Mclock, and the GFX clock. Just like on Ryzen 7000 Raphael CPUs, the Ryzen 8000 Phoenix 2 processors support asynchronous Eclk. Eclk stands for external clock and is exactly what the term suggests: external clock generator inputs. The external clocks are inputs to the FCH. There you can configure how you want to use the external clocks. In addition to the standard internal CGPLL, Phoenix 2 supports up to 2 external clock modes. In Eclk 0 mode, an external 100 MHz reference clock is used for both the CPU and SoC PLLs. In other words, it's a reference clock that affects the CPU core clocks and the PCIe as well as the SATA clocks. In Eclk 1 mode, there are 2 distinct external 100 MHz reference clocks. One clock provides the 100 MHz input for the core PLL, and the other provides the 100 MHz reference clock for the SoC PLLs. The overclocking approach with Eclk is the polar opposite of what we're used to with AMD Ryzen CPUs. As I demonstrated in overclocking strategy number 2, typically we would use a negative curve optimizer, and that would push the CPU to try and run higher frequencies. With Eclk, we still build on top of the factory-fused VFD curve, but adjust the frequency ceiling by adjusting the reference clock. For example, if there's a VFD point for 4.5 GHz at 1 volt at 50C, with an Eclk of 105 MHz, the actual point will be 4725 MHz at 1 volt at 50C. I already mentioned it a couple of times, but the AMD Phoenix 2 core clocking is a little bit odd due to the mixed Zen 4 and Zen 4C core types. Let's have a look at how this all works. We can distinguish 2 scenarios. One where either C or D cores are active, and 2 where both C and D cores are active. In the scenario where either C or D cores are active, and it doesn't matter how many, the behavior is pretty simple. Each core type can boost to its programmed Fmax. At stock, that's 5050 MHz for the C cores and 3700 MHz for the D cores. In the scenario where both C and D cores are active, the behavior is a little bit more complex, as the C and D cores will operate at a fixed relative ratio. At stock, the C core operates at 1.25x the frequency of the D core. This ratio becomes 1.50x when we set a Fmax boost override of minus 300 MHz or lower. As I mentioned, it's a little bit odd that cores within the same CCX can run at different frequencies. The way this seems to work is that the reference clock and the frequency ID or FID of a CCX must be the same. However, we can have a core-specific divider ID or DID. Let's have a look at a couple of examples. Let's say the reference clock, VCO, is 200 MHz, the FID is 185, and the DID is 8. In that case, the operating frequency is 4625 MHz. By using a DID of 10 for the D cores, the frequency becomes 3700 MHz. Incidentally, this is the default frequency for the Ryzen 5 8500GE. Let's say we increase the frequency by configuring an Fmax boost override of plus 200. In that case, the NT Fmax limit for the C cores is 4775 MHz. This can be set with an FID of 191. With the D cores using a DID of 10, this frequency is then 3820 MHz. We can also confirm this frequency when checking the operating clocks in Windows with hardware info. This also holds true when the C to D core NT ratio is 1.50x. For example, let's say we set the Fmax boost override to minus 400 MHz. In that case, the NT Fmax limit for the C cores is 4650 MHz. This can be set with an FID of 186. With the D cores now using a DID of 12 to get the 1.50x ratio, their frequency is then 3100 MHz. We can also confirm this frequency when checking the operating clocks in Windows with hardware info. As a final note to this topic, the difference in divider ID also adds further granularity to the CPU core ratio. We're all used to Ryzen CPUs having a core ratio granularity of 25 MHz, but that's not exactly the case with AMD Phoenix 2 processors. If we set the Fmax boost override to minus 375 MHz, for example, the NT frequency for the D core is 3116 MHz. That's a frequency granularity of 16.67 MHz. Anyway, now that we've learned everything there is to know about AMD Phoenix 2 clocking, let's have a look at the voltage topology. AMD Phoenix 2 voltage topology is similar to that of previous Ryzen processors. As per usual, the processor relies on an internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDD-CR voltage rail provides the external power for 3 internal voltage regulators. The VDD-CR CPU voltage rail provides the voltage for the CPU cores within the CCX. The voltage rail can work in either regular or bypass mode, but it is always in bypass mode on Phoenix 2. That means the voltage of the cores is always equal to the VDD-CR external voltage. Since the D cores have a much higher transistor density, they can't handle too much voltage. Therefore, AMD has implemented a voltage limit of 1.2 volt. In practical terms, the external VDD-CR voltage rail is regulated to 1.2 volt when a D core is active. This also limits the voltage supplied to the C cores and therefore will restrict its operating frequency. When all D cores are power gated, in sleep mode, then the external VDD-CR voltage rail can provide a higher voltage to the C cores to support its higher frequency capabilities. Due to this voltage limitation requirement, unfortunately, we are unable to change the voltage in the BIOS. The Eclk tuning process for Phoenix 2 processors is pretty complex, primarily because we have mixed core types and mixed Fmax boost limiters. The goal for this overclocking strategy was to maximize the multi-threaded performance, and the key limiting factor, ironically, is the C-core 1T maximum frequency. Basically, the C-cores have an overclocking headroom of about 5.2 GHz only. So we need to find the optimal setting that maximizes the D core frequency while making sure that the C core frequency doesn't go over 5.2 GHz. In case of the Ryzen 5 8500GE, that's at plus 100 and plus 125 MHz boost override. For these two settings, the frequency deltas are as follows. By minimizing the frequency delta, we can increase the D core frequency the most until the C cores become unstable. The testing process is very similar to what we use for curve optimization, with one major caveat. Because we increase the frequency of the VFD curve, we also may need to increase the voltage, and we can use that by using a positive curve optimizer. I found that the maximum stable overclock was with 101 MHz Eclk frequency, which combined with an Fmax boost override of plus 125 MHz yields 1T C core and D core frequencies of 5227 MHz and 3863 MHz, and NT frequencies of 4823 MHz and 3858 MHz. In addition to the CPU core overclocking, I've also improved the memory performance subsystem just a bit by increasing the Fclock frequency to 2600 MHz and increasing the memory clock to DDR5 6600. Since we're still running the Uclock and Eclk in sync, that means the memory controller is also running at 3.3 GHz. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO Tweaked. Set Eclk mode to asynchronous mode. Set BCLK to frequency to 101. Set memory frequency to DDR5 6600. Switch to the advanced menu. Enter the AMD overclocking submenu and click Accept. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2600 MHz. Set Uclock diff1 mode to Uclock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 125. Enter the Curve Optimizer submenu. Set Curve Optimizer to Per Core. Set Core 0 Curve Optimizer sign to Positive. Set Core 0 Curve Optimizer magnitude to 15. Set Core 1, 2, 3, 4, and 5 Curve Optimizer sign to Negative. Set Core 1 Curve Optimizer magnitude to 20. Set Core 2, 3, and 5 Curve Optimizer magnitude to 25. Set Core 4 Curve Optimizer magnitude to 5. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to Enabled, then save and exit the BIOS. We reran the benchmarks and check the performance increase compared to the default operation. We have to do a lot of fine-tuning to push the CPU core frequency up marginally. That translates into a small but noticeable improvement in the performance across single-threaded and multi-threaded workloads. The geomean performance improvement is plus 7.75%, and we get a maximum performance improvement of plus 17.83% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU C-core effective clock is 4776 MHz, and the average CPU D-core effective clock is 3820 MHz. The average CPU core voltage is 1.191 volts. The average CPU temperature is 75 degrees Celsius. The average CPU package power is 75 watts. When running the OCCT CPU SSE stability test, the average CPU C-core effective clock is 4797 MHz, and the average CPU D-core effective clock is 3838 MHz. The average CPU core voltage is 1.199 volts. The average CPU temperature is 68.4 degrees Celsius. The average CPU package power is 72 watts. The boost frequency at one active thread is 4227 MHz and stays there when up to 4 C-core threads are active. When D-cores become active, the average boost frequency gradually trails off to 4209 MHz when all cores are active. The 2 C cores can boost to slightly over 5.2 GHz, and the 4 D cores can boost to nearly 3.8 GHz in single-threaded workloads. Alright, let's wrap this up. I was very excited to finally try an AMD Phoenix 2 processor, because the architecture is so unique with the Zen 4 and the Zen 4 C cores. Though we should refer to those as the classic cores and the dense cores in AMD nomenclature, which is a bit odd because the C cores aren't actually Zen 4 C architecture. I don't have that much to comment about the performance improvement because it's very similar to the other Hawk Point processors that I've already overclocked on this channel. The main limiter for increasing the performance is the capability of the Zen 4 cores. And I can't really comment whether that's down to the specific architecture or the manufacturing process. Essentially, we're limited to 5.2 GHz. When it comes to fine-tuning the Phoenix 2 performance, it gets a little bit complex. Not just because of the 2 core types, the Zen 4 and the Zen 4C cores, but also because each of these core types have different limiters. And they don't just have a single Fmax limiter, they have a limit for 1T and they have a limit for NT performance. In addition to that, there's voltage limiters that makes it additionally complex to chase higher performance with the Phoenix 2 processor. Anyway, that's it for this video. I thank you for watching, and I also thank the patrons for their support. We'll also have a look at the integrated graphics of this Ryzen 5 8500GE processor in a future video. Until then, see you next time.